Hello everyone. Today I will introduce the OTA section of the BLE SoC series. The introduction will focus on the following four aspects: OTA Overview, OTA Scheme, Transmission Process, and OTA Demo Usage. First is the OTA Overview. OTA stands for over the air and is a technology used for data transmission and software updates through wireless communication. The main advantages are as follows. 1. It fixes bugs or vulnerabilities in the device software, ensuring smooth operation and reducing the chances of malfunctions. 2. It can add new features or improve existing ones. 3. It optimizes device performance, allowing our devices to run faster and more efficiently. 4. It helps enhance device security to protect them against new threats. The OTA process involves multiple roles, each playing a critical role in the update cycle. First is the cloud server, which is responsible for storing the upgrade files. Next are the mobile devices, which initiate the upgrade instructions and manage the update progress. Finally, there is the target device, namely the SoC end, which receives and executes the updates. Next, I will introduce several OTA schemes for the Realtek BLE SoC series. First, we have the dual bank scheme. Its feature is using two banks as firmware storage areas that back each other up. The main advantage is preventing device malfunctions during updates. If the update fails, the system automatically rolls back to the previous firmware version, ensuring the device operates normally. Next is the single bank scheme. In this scheme, there is a backup area that temporarily stores the new firmware when an update is needed. Once the firmware is successfully transferred, the bootloader transfers the new firmware from the backup area to the operating area, and finally, the device is restarted to run the new firmware. The single bank scheme can be further divided into two schemes. The first is single image upgrade, where only one image is upgraded at a time. The next image will be upgraded only after the current image has been upgraded, successfully verified, and activated upon reboot. The second is the multiple image upgrades. When the size of the OTA temp area is sufficient to accommodate multiple images at once, multiple images can be upgraded simultaneously. When writing image data into the OTA temp area, the system calculates whether enough space remains for the next image to be written. If so, the next image is written. If not, the device is first restarted to migrate the OTA temp area's data to the operating area, and further file upgrades occur after the copy activation takes effect. Lastly, we look at the user data upgrade scheme. In this scheme, the image is written directly to the flash area that stores user data during an upgrade, and there is no backup area for support. The following will introduce these OTA schemes using the RTL87X2H as an example. First, let's introduce the dual bank scheme, with the flash layout shown in the figure. The feature of this scheme is that the size of OTA Bank 1 is identical to that of OTA Bank 0. The system decides which bank to run based on the version number of the OTA header image in the OTA bank. All images in the OTA bank are upgradable, including the OTA header, ROM patch, Secure Boot Loader, BT Stack Patch, Upper Stack, and App. This scheme has several notable advantages. First, after the upgrade is completed and the system is restarted, the program can directly start running from the new bank, making the transition process of the OTA upgrade extremely quick. Secondly, since the system always retains a backup bank, even if a fault occurs during the OTA process, the SoC can continue to run stably, providing a reliable error protection mechanism. However, the dual bank scheme also has its limitations. The primary challenge is the significant increase in flash usage, as it requires reserving enough storage space for a second bank. This can be an important consideration in devices with limited storage resources. Next, I will introduce the single bank scheme. The characteristic of this scheme is that the size of OTA Bank 1 is set to 0. To support upgrades, the size of the OTA temp area must be larger than the size of the largest image in the OTA bank. In this scheme, we can upgrade the ROM patch, secure bootloader, BT stack patch, upper stack, and app in the OTA bank. However, it is important to note that the OTA header image cannot be upgraded in this scheme. The main advantage of the single bank scheme is that it relatively saves flash space. This is because it does not need to reserve space for an additional bank, thereby effectively reducing storage requirements. However, this scheme also has certain limitations. The primary one is that once the OTA transfer is complete, the bootloader needs to copy the data from the OTA temp area to the operating area, then restart the device to apply the new firmware. This process increases the reboot time required to complete the OTA upgrade, which may be inconvenient for certain application scenarios. As shown in the right figure, the app image with asterisks to be upgraded is first transferred to the OTA temp area. After the transfer is complete, a reboot copies the app image with asterisks to the app area to run the new firmware. Next, I will introduce the multiple image upgrade scheme in a single bank. This scheme allows the transmission of multiple images in a single reboot, effectively enhancing the efficiency of OTA upgrades and avoiding the delays and system interruptions caused by multiple reboots. To achieve this functionality, we need to perform specific configurations in the SDK. Specifically, it requires configuring the support temp combined OTA macro in the board.h file. This configuration ensures effective management and transmission of multiple images during the OTA process. Next, let's discuss the SoC support situation. The level of support for this feature varies across different chip versions. For RTL87X2C, the common patch does not support this functionality, and a customized patch is needed to achieve it. However, for RTL87X2E, H2G, this feature is supported by default in the ROM, which can be used directly without additional customization. As shown in the right figure, the upper stack and app image with asterisks to be upgraded are first transmitted to the OTA temp area. Once the transmission is complete, a single reboot can transfer the upper stack and app image with asterisks to the operating area of the OTA bank, enabling the new firmware to run. Finally, I will introduce the user data upgrade scheme. This scheme directly writes the image into the flash area where user data is stored, without an OTA temp backup region. Why is the OTA temp backup region not needed? This is because user data usually contains information that does not affect system functionality. Even if a sudden power outage occurs during the upgrade process, the loss or corruption of these data will not result in the device becoming bricked. Therefore, this upgrade mechanism can tolerate higher risks. It does not have to worry about causing significant impact on the device. However, when adopting this mechanism, it is still necessary to balance the relationship between data integrity and system stability. This ensures that users can accept the potential risk of data loss. As shown in the figure below, upon successful upgrade, the user data 1 and user data 2 image with asterisks will directly overwrite user data 1 and user data 2. The previously introduced schemes are all for uncompressed images. Next, I will introduce an image compression scheme. It aims at improving the space utilization of small capacity flash. Currently, this scheme only supports single bank. The compressed OTA scheme ensures efficient device operation by effectively optimizing flash resources. In this mechanism, we use the LZMA compression algorithm, known for its excellent compression performance. By compressing the image before transferring it to the OTA temp area, we can significantly reduce the space occupation in the OTA temp area. The compression ratio is approximately 70%, meaning that firmware requiring large space can be compressed to a much smaller size, enabling more functionalities within limited space. As shown in the figure, the app image to be upgraded is only 140 kilobytes after compression, and then it is transferred to the OTA temp area. Once the transfer is complete, the system will reboot and decompress this file to 200 kilobytes, then copy it to the operating area. This scheme improves space utilization efficiency and provides a more flexible solution for device upgrades. Currently, this OTA compression scheme supports compression of only upper stack and app images. Other types of images cannot be compressed using this scheme at this time. Additionally, in terms of flash layout, 12 kilobytes of space must be specifically reserved for app data 1 to store the decompression algorithm. Therefore, it is important to consider this additional space requirement when planning the flash layout. Regarding the usage of this scheme, the first aspect is patch support. The common patches do not support this feature and require customization. Next is SDK support. By default, the SDK does not offer support for this compression scheme, so additional configuration is necessary to enable the related features. In terms of IC support, the OTA compression scheme is currently supported by RTL87X2C, D, E, H. Support for RTL87X2G will be provided in future versions. Next, I will introduce two different OTA transmission protocol modes, silent OTA and normal OTA. First is the silent OTA. The advantage of this mode is that the image upgrade process does not affect the use of the device's original functions. Users can continue with their daily operations on the device while the upgrade proceeds quietly in the background. Once the upgrade is complete, only a brief restart is needed for the program to automatically switch to the new features. Silent OTA aims to provide a smoother user experience by minimizing the disruption to device use during maintenance. Next is the normal OTA. Compared to silent OTA, the normal OTA offers greater reliability in terms of functional stability. However, its upgrade process requires the device to be switched to DFU mode. During this time, the device's original functions become temporarily unavailable until the upgrade is complete. This means that users will not be able to use other functionalities of the device during the upgrade. Nonetheless, this mode ensures functional stability, making it suitable for upgrade scenarios where simultaneous use of device functions is not required. By comparing these two modes, we can see that each has its pros and cons. The choice of OTA mode can be determined based on specific application scenarios and user needs. Here is an explanation of the image flag, where the image header includes only two OTA-related bit fields, not ready and not obsolete. First is not ready. This flag indicates whether the image is valid. In files that are released, compiled, or generated through tools, the not ready field in the image header is set to 0 by default. When an image is transferred via Bluetooth to the OTA temp area, there is a risk of power interruption. Therefore, before writing to the OTA temp area, the not ready flag should be changed to 1 and then written into Flash. Once the image transfer is complete and the image integrity is verified successfully, the not ready flag in the OTA temp area image should be set to 0, indicating that the OTA temp area image is valid. Second is not obsolete. This flag indicates whether the image in the OTA temp area is obsolete. In a default compiled image, not obsolete is set to 1. When bank switching is supported, the not obsolete flag is irrelevant during the DFU process. When bank switching is not supported, after the DFU upgrade is completed, the startup code checks that not ready is 0 and not obsolete is 1. At this point, the image is moved from the OTA temp area to the corresponding image's running area within the OTA bank 0. After the successful move, the not obsolete flag in the OTA temp area image is set to 0 to prevent repeated transfers. This flag system helps manage the validity and status of images in the flash memory during OTA updates, ensuring that only fully transferred and verified images are used, and preventing outdated or partially transferred images from being executed. Next, I will introduce the transmission process of the OTA upgrade. The first step is to enable the buffer check feature to ensure the transmission proceeds smoothly. The second step involves reporting information about the device's image, including the image ID and the current offset. In the third step, we initiate a device firmware upgrade. During this step, essential information, such as IC type, image ID, and payload length, is sent, and the Not Ready flag is set to 1, indicating that the device is not yet prepared to activate the new firmware. The fourth step is receiving the firmware. The device will receive the entire firmware file. The fifth step involves verifying the integrity of the firmware. Once the firmware is received, its integrity is checked using the SHA-256 algorithm to ensure it hasn't been tampered with and is valid. Upon successful verification, the Not Ready flag is reset to 0. The final step is activating the new firmware. After the device activates the new firmware, it will automatically restart to run the latest version. This series of steps ensures the OTA upgrade process is secure and effective. Then, I will introduce how to using the OTA demo, incorporating the following tools. First, there's the Flash Map Generate tool, which is used to plan the flash layout and generate the flashmap.ini, flashmap.h, and the OTA header file. Second, the MP-Pack tool is utilized to package the OTA upgrade files. Additionally, there's the OTA tool, which is used for conducting OTA upgrades via Android or iOS devices. Lastly, the paths for the OTA demo projects are designated as shown above. First, let's take a look at how to use the Flash Map Generate tool. Using the single bank as an example, I will explain the process of generating the flashmap.ini, flashmap.h, and the bank 0 OTA header files. First, select the appropriate flash size to ensure that the configuration meets the device's requirements. Second, in the Support OTA Switch option, select Disable to align with the current configuration. Third, set a 2-level flash layout to ensure that the memory partition meets the application requirements. Fourth, click the Confirm button to complete the flash layout setup. Next, modify the version information of the OTA header image in the version section. Finally, click the Confirm button to generate the required flashmap.h, flashmap.ini, and bank 0 OTA header files. Next, I'll explain how to use the MP-Pack tool to generate a package file. To begin, select the For OTA option to ensure that the generated file is suitable for OTA upgrades. Then, load the generated flashmap.ini file. Next, click the Browse button to load all the image files that need to be upgraded. Finally, click the Confirm button to generate the package file. By following these simple steps, you can successfully complete the generation of the package file, ensuring full preparation for the upcoming OTA upgrade. Finally, I'll introduce how to use the OTA tool, using the Android OTA tool as an example. First, load the package file generated in the previous steps into the File Path section of the OTA tool. Next, click the Upload button to start the upgrade process. This action will transfer the package to the device and begin the OTA update. Once the upgrade completes, verify that the new image has been successfully activated on the device. This confirmation ensures that the update process was successful. This process is simple and efficient, helping to ensure the smooth execution of software updates. The above is the content of BLE SoC OTA Introduction. Thank you.